Thank you very much. It's a privilege to be here. I'll be taking off very much where Martin Lees ended, showing why there's a scientific basis for rapid action on climate change, given that it's a systemic challenge, which in fact originates from a new situation for global human development in an era of rapid global change. Now, this systemic challenge in fact starts with a social dimension. It starts very much in the end that was pointed out in the previous session, that we are today 7 billion people. We're committed to 9 billion people by 2050, but it also has a dilemma. It has an equity dilemma that the predominant source of the negative environmental trends we've seen so far have predominantly been caused by the rich minority on the planet. The 20% that jumped onto the industrial revolution in 1750 and that has enjoyed the fossil fuel-based exploitation of wealth creation so far, and that we have 80% of the population on the planet with a right to development and a very positive momentum towards human well-being and development, which largely is aspiring to an unsustainable lifestyle which is similar to the past. We have a climate pressure on the planet which has also a triple dilemma, which is that the policy interpretation of the climate science is that it would be enough to stabilize greenhouse gas concentrations at 450 ppm to avoid dangerous warming exceeding 2 degrees. Now, there's very little scientific support that there is an equal sign between 450 ppm and 2 degrees. In fact, later science, and Jim Hansen is here and we'll talk more about that, I'm sure, is that we may in fact have to stabilize at 350 ppm of CO2 concentration, or roughly 400 ppm of CO2 equivalents, to have a reasonable chance of avoiding 2 degrees. And the International Energy Agency showed that we are at a very rapid momentum towards 550 ppm and beyond. You would wish this disturbance to occur on a resilient planet, on a planet that is strong and able to buffer this pressure. But unfortunately, the UN Millennium Ecosystem Assessment and the following work of the Economics of Ecosystems and Biodiversity team shows conclusively that over the past 50 years, humanity has undermined ecosystem functions and services more rapidly than ever in the history of humans on the planet. And these ecosystem functions and services include issues such as the ability to regulate climate, the ability to regulate air quality, pollination, and water flows. So we have an ecosystem crisis occurring simultaneously with a climate challenge. Now, as if this was not enough, complex systems dynamic research and resilience science shows over the past 30 years that nature is not behaving according to the economic paradigms and governance paradigms that we've put in place. We assume that nature changes linearly, incrementally, and therefore predictably and also controllably under our pressures. But in fact, most science shows today that surprise is universal, that ecosystems from local wetlands to monsoon systems to rainforests have multiple stable states separated by thresholds, and that we can, under long periods, so to say, be privileged to benefit from stable systems because of the ability of systems to stay in a desired state, but a small trigger can then quickly push systems across to new undesired states. This is a new cocktail for human development. It's so serious, in fact, that the Nobel Prize laureate Paul Crutzen, one of the 3 scientists who identified the depletion of the ozone hole layer, has been identifying the risk of humanity having entered a new geological era. We may be exiting the Holocene and moving into the Anthropocene, where humans are the predominant driver of change at planetary scale. What's the evidence of this? Well, unfortunately, the evidence is ample. And normally we focus on this evidence, namely the hockey stick pattern of carbon dioxide concentration. But you are certainly well aware that this is not the only negative trend on the planet. You have the sister of the carbon dioxide curve, which is, of course, temperature rise. But then you have the similar curve on nitrous oxide, which originates from industry and modern agriculture. Methane, which also originates from land use change. Ozone depletion, which is the only curve humanity has been able to start bending through the Montreal Protocol. The frequency of climatic disasters, overfishing of the oceans, eutrophication of coastal areas, again from modern agriculture predominantly, deforestation, agriculture expansion, and finally the issue that's been on the table for the last 2 weeks in Nagoya, the 6th mass extinction of species on the planet. The first one caused by humans, one of the other 6 being the extinction of dinosaurs 65 million years ago, which is a massive change of the sustainability on the planet. Now, this is an enormous price tag that humanity has caused on the planet, and of course it has had huge human benefits over the past 100 years. This is one way of illustrating the remarkable journey we've made in terms of creating wealth. On the x-axis here you have the number of children born per woman, and on the y-axis you have life expectancy in terms of years. And look at where the world is. The circles here are countries. Up on the left-hand desired corner, life expectancy has never been so good, the number of children per woman never so low as presently. The blue countries here are the most vulnerable countries in Africa and the most unstable economies in the world due to poor governance. So of course there is a tremendous positive side of this coin, which is encapsulating why the challenge is so difficult to have sustainable growth in the future, because we have, so to say, exploited the planet to huge human benefits. But the price tag is now to a point where we need to really consider the new agenda of development in the Anthropocene. May we be approaching a point where we may be eroding this well-being that we've created. And Will Steffen, who will be talking later today, did a seminal synthesis of the hockey sticks 2004, showing that they're all bending roughly at the same time, in the mid-50s. Mid-50s can be considered as the point of the great acceleration of the human enterprise. 10 years after the Second World War, we're 3 billion people, something happens to the industrial metabolism where we for the first time start seeing a global imprint. Now, 60s and 70s, with the Club of Rome report, we were just at the start of this curve. What a phenomenal foresight of a few individuals to foresee that this would continue. But now we have the scientific evidence for the first time to say we have really reached a very high point in this negative exponential curve. Moreover, when you enter the disciplinary science of climate, of oceanography, of ecological sciences, hydrology, most of them indicate we have to bend the curves this decade. We have to bend the carbon dioxide emissions curve by no later than 2015. We have to stop the extinction of species during this decade, etc. So we may have entered the most decisive decade of modern human history, the decade when we need to bend the curves to secure the wealth we've created so far on the long term. Now, linked to this is not only the pressures from accelerated curves onto systems that fundamentally provide social and economic development. The key issue is also to couple this with nonlinear change. There is so much research today, a battery of evidence to show that systems have, shown here in cup and bowl diagram, an inbuilt resilience, shown with the depth of the cup, to withstand disturbance. Systems from coral reefs, clear water systems, savannas, under long periods of exploitation remain apparently stable, but lose gradually their ability to stay in a desired state. When the cup gets too shallow, a small trigger can have the system topple over, and it may be stuck in a completely new undesired state if you have a feedback. And the feedback is a self-reinforcing factor which makes a chain structure. It's so clear for hard coral reef systems which, under pressure from overfishing, eutrophication, global warming, ends up in a situation where soft coral systems take over, which changes the logic through self-eutrophication. Similar in lake systems where predators disappear, phytoplankton take over, self-reinforcing a eutrophied state. And how hydrology changes when you're drying out systems from rainforests potentially to savannas, or savannas potentially to steppes. So we're starting to see a growing insight that we may be lulling ourselves into a comfort zone because systems appear to be stable while they are increasingly becoming vulnerable, and that the resilience is one virtue of the planet, but also a risk for us of not seeing these dynamics. One very powerful example is this one, which is the Arctic. This is how we'd like to see the Arctic. This is how scientists have seen the Arctic in most research. But as you know, in 2007, which Martin pointed out, we suddenly had a situation like this. A very abrupt, to science surprising, shift in loss of summarized extent. The drama here is that there's still a question whether there's a threshold, but the feedback is so well known. Change of reflectivity of the surface, creating more absorption of solar radiation, and thereby self-accelerating a potential new state of the Arctic. So this is one example how thresholds are being now observed not at the local ecosystem level alone, but more at the regional to the larger scale. So the question then is, what risks is that posing to humanity? Well, on climate, the risks are increasingly understood, but there's still a large degree of uncertainty. This is profoundly showing that case. This is the state of knowledge in terms of climate risks in 2001 with the third assessment of the IPCC. Here you have degrees warming from 0 to 5 Celsius for the planet, red high risk, white low risk. And to the left you see the risks of undermining ecosystems, which showed in 2001 the scientific state of the art that the risk was at an average warming of roughly 3 degrees. That was the point at which we may be risking undermining, for example, the marine tropical systems in the world. The column to the furthest right there shows the risk of large-scale discontinuities, the risk of human-induced climate catastrophes. And the risk was set as state of the science at that point at 4 to 5 degrees. One should remind ourselves that we go in and out of ice ages as a plus-minus of roughly 3 to 4 degrees. So these are large, large shifts. Here is the state of knowledge in the post-IPCC from 2007 onwards. And as you see, the whole risk pattern is going down. So the more we learn of the complex self-adaptive planetary system, the more we realize the vulnerability of these kind of nonlinear changes. And with the risk for ecosystems climbing down to 2 degrees, and with the risk for large-scale discontinuities being down at the 3-degree level. So science can no longer exclude large-scale undesired change already at 3 degrees warming.